Morning, everyone. So we're going to continue with our review with a look at our dynamics chapter. So dynamics here, that word in general, dynamics means sort of studying the mechanics of the system. And what we use here is we use the lens of forces. Forces, if you remember, are just simple pushes and pulls, or push or pull. Because that can be applied in many different directions, we know right away forces are vectors. A vector here has both magnitude as well as direction. We saw, especially in this chapter here, we did those free body diagrams here. Because I have arrows directly pointing which way I'm pushing or pulling, I could avoid, like in our first chapter, we had to worry about a lot of positives and negatives here. These ones here are typically measured with units newtons. 1 Newton is going to be equivalent to about, like, let's say an average size apple. If you lift up the apple, that's about the force for 1 Newton. Newton is actually a derived unit. It actually comes from 1 kilogram meter per second squared. In terms of your forces here, there's two main types of forces. Some forces were what we refer to as contact forces. Think about forces like friction. Friction is when two surfaces sort of rub past each other here. Friction is always opposing to motion. We saw a calculation for that one there. Where the other type of force here is actually a non-contact force, or sometimes they call these as action at a distance forces. So they can actually act when things are really far away. So for example, gravity was an example of that one there. We then went through a quick detour of a few fundamental forces since our universe began. There were 4 forces. We started off with gravity. If you go into physics, you're going to learn gravity as a warping of space-time. It's going to be a little bit weird. Electricity and magnetism were sort of two sides of the same coin. Physics 12 will flesh that out a lot more, how we can actually use electricity to generate magnetic fields, or changing magnetic fields to actually create electrical current. There's 2 other fundamental forces, the strong nuclear, the weak nuclear force here. Pretty much it's the force that's holding all our nuclei together. Were not for those things, our atoms would totally disintegrate. But the forces that we learned were a lot more sort of big scale picture, some combination of those fundamental forces. For this section here, we did it through really systematically. Yes, we started off with what's referred to as a free body diagram. Just want to remind you of this. So a free body diagram, they can shorthand this one here in FBD. A free body diagram here, although realistically your objects may actually have some space to them. If I apply a force, let's say on the top of this object or on the bottom of this object here, that might be a little bit different. We sort of ignored that and we sort of said, let's pretend all of your mass is squeezed into a tiny, tiny point. That point there is going to be called your center of mass. And what you're going to show me is all the arrows that act on just this singular point. So if this object were just sitting there, we would be able to say, well, there's gravity, right? Fg is going downwards. In the earlier chapter, we used negative for there, but since I already have a diagram, I already have this arrow pointing down. I don't necessarily need to have that negative there. Well, if this were the only force, we'll see from Newton's 3 laws again, if there is an unbalanced force, there would be acceleration, and yet we sort of know the answer here. Wait a second. This thing here is just sitting on the ground. There has to be something supporting it. Whenever you're on the ground, you actually have a normal force. The normal force, the only trouble here is, yes, it is supporting, it's pushing perpendicular to the surface, but there's no equation for normal force. It just pushes what it needs to. Okay? So looking at these 2 forces in a little bit of detail, Fg, right, we always have a formula for force of gravity. This was actually a simplification from our universal gravitation formula. We'll see it towards the end here. Fg is just m times g. It actually gives us a proportional relationship. M here is mass. Mass is measured in kilograms. It measures the amount of material or the amount of substance that you're made up of. Whereas for force, this one here is our push or pull. This one here is measured in newtons. So we know it's proportional. If we're on the Earth's surface, this g is the acceleration due to gravity. This was at 9.8. In the last chapter I mentioned we use negative, but since I already have the arrow here, I don't necessarily need to have that negative anymore. Let's say we had an elevator style question. So starting off with an elevator, let's say temporarily this elevator here is actually going to accelerate upwards at, let's say, 2 meters per second squared. Okay? To sort of avoid the hassle of positives and negatives, we started thinking of this as a tug of war. So if I were just standing on this elevator here, right? It's the tension in the cable that's actually allowing me to have some net force going upwards. Well, there's two forces that allow me to actually go upwards, right? My elevator later on would be here, elevator later on would be here, right? I'm going to actually go upwards. There's only two forces that act on me. Gravity tries to pull me down towards the bottom of the elevator. The ground of the elevator is pushing me upwards. Which of these forces have to be bigger for me to actually have a net force going upwards? Well, in this situation, the normal force actually has to win out. We're actually going to say the net force, this is the overall unbalanced force. Careful, this one here is not its own force. I can't say, oh, it's the net force that does this. The net force is what's remaining behind based on the tug of war. So in this case here, the tug of war is between Fn and Fg. Usually I go bigger minus smaller to avoid problems with negatives. So in this case here, I know my normal force has to be bigger. So my normal force has to win out gravity. And we're going to see in Newton's second law here, the F net is equal to ma. Numerically here, yes, F net is the thing that actually causes the acceleration. Whenever I go bigger minus smaller, I can then keep this acceleration here as positive. Okay. Sometimes it's going to be Fg minus Fn. It really depends on the situation. Okay. So there's the force of gravity. There's an example of how you find normal force. The normal force here, let me remind you here. So the normal force, we're going to use F subscript n. That force there is perpendicular to the ground. Okay, perpendicular to the surface. So for the longest time here, our surfaces were just flat across, so it was just pushing directly upwards. Towards the end of this chapter, we started going on a slant. The normal force would then push perpendicular to that slant there. Let's do a few scenarios here. If I'm standing here, let's say gravity is pulling me down 300 newtons. What's the normal force going to be? Well, if I'm just standing there, I know nobody wins. The normal force would have to be 300. What if a bird perches on my shoulder here and tries to lift me upwards? A bird comes behind me and actually pulls you upwards at 50 newtons. Okay. First thing you need to say is the bird pulling hard enough to actually lift you off the ground? Well, if gravity is still pulling you down 300 newtons, well, no, the bird is only pulling 50. But the bird is doing something. It's trying to perch on your shoulders and try to lift you up a little bit. If the ground continued pushing 300, then with the bird and the ground, you'd come off the ground. But we just said the bird can't pull hard enough, so the normal force just thanks the bird a little bit here. The normal force changes a little bit lazy. It only supplies 250, so that the 250 plus what the bird is doing, it ends up canceling the 300. Okay, so normal force does only what it needs to. Why were we concerned about normal force? Was this actually help you calculate friction? Friction force here is technically in our diagrams a horizontal force. It's a little bit weird how come friction, Ff, is actually given by mu times Fn? Isn't Fn a vertical force, right? Ground pushing up, and whereas friction is actually stopping things side to side. I thought we went through this whole notion, well, the up and down doesn't affect the side to side. Well, what's actually happening here is, in some sense, that's still correct. The vertical can't affect horizontal. But what's happening here is, let's imagine my Fn is larger. What's going to happen is between two surfaces, no matter how smooth surfaces feel macroscopically, there's all these little microscopic grooves that are on the top surface. There's microscopic grooves that are on the bottom surface as well. If you increase the gravitational force, if you end up sitting on this object here, now the grooves end up interlocking a little bit more tightly with each other. That's going to make it harder for you to get these grooves here out from each other. So what we define here is something called a friction coefficient. Or coefficient of friction. So friction coefficient, it's a number that describes the roughness here. We're going to use mu for it. We did this in a little bit more detail that we had said, well, mu k, or so let's do mu s first. Mu s is for static friction. Static means the object here wasn't moving. This is just to get the object moving. So our grooves are sort of maximally interlocked here. It's really hard to actually slide one surface from the other surface. Then once the object here starts sliding along here, we don't really give it a chance for the grooves to really interlock. Then we're going to actually end up with a mu k. That's going to be called the kinetic friction. And this is the amount of roughness that it experiences as the object slides. So we really don't let the objects actually interlock together. Typically speaking, the kinetic friction should be less than the static friction. For simplicity in most questions here, we're just going to condense this into just one and the same mu coefficient. If it was at rest, you can interpret it as static coefficient, but usually we don't need that detail. What I did want to just review with you here is this friction coefficient, remember, is a maximum friction. Friction, like normal force, is a little bit lazy. Even though based on my grooves, I might be able to calculate how much total it might stop motion, friction only applies enough to stop motion. That's what it's against. If there's no motion, friction doesn't need to push any beyond that. So let's do a quick picture here, and then we'll do a worked out example. Let's say I apply a force of 20 newtons going to the right. Let's say when I calculated my formula, the maximum friction, based on the normal force, based on the coefficient, based on the roughness here, maybe my maximum friction was some 100 newtons, right? So here I am, I'm trying to apply a force, I'm trying to pull this object to the right, and yet the friction force is too intense. If this were the case, I'm trying to push to the right. If friction maxes out against me, there would be a net force in the left-hand direction, which doesn't make any sense. Friction says, just like the bird analogy, oh, look at you, you're only actually pulling 20. That's nowhere near what the 100 I can go against you. Friction is going to drop down to 20 in the opposite direction. You can either put a negative there or just show it with the arrow. If friction goes against you 20 here, it's already canceled out your net force. If there's no net force, there's going to be no acceleration. That's done. What if I start pulling harder? So what if I start pulling, let's say, 120 newtons? Well, this time friction wants to stop motion, but we just said the maximum friction was only 100 newtons. This time when we go bigger minus smaller, we have a net win of going in the rightward direction. That one there is 20 newtons forwards. Now that one is a net force. There's an unbalanced amount of force that's going to cause this one to actually move to the right. So friction only pushes as hard as stopping motion. At this point here, I just want to recap with you Newton's 3 laws. Right. He actually summarized a lot of this dynamics work for us here. First one, essentially, objects continue at uniform velocity or uniform motion as long as no net external force is applied. So if your net force is 0, you're just going to continue at uniform velocity. Remember, constant velocity doesn't necessarily mean 0. This could mean, yeah, we're at rest, it's just sitting there at 0, but I could be actually moving. But as long as I'm moving, let's say at 10 meters per second, earlier I was 10, a little bit later I'm 10, a little bit later I'm 10, that's also a situation of constant velocity. That's when there's no net force. You do not need net force for motion. What do you need net force for? That comes Newton's second law. If there is a net force, the F net is actually proportional to m times a. Now be careful again, this net force is not a force. This is not a push or pull itself. You can't be like, oh, it's the net force that pulls this way, or the net force that pulls this way. This is just what's left over from the tug of war. So you can write that down here. This is left over from the tug of war, from the bigger minus smaller. So what this formula tells me here is if there is an unbalanced force, if there is something left over, this will cause masses to accelerate. So forces will cause speed to change. You're no longer going to be uniform anymore. The third law here, which is sort of the most well-known, is sort of equinopposite. This is the one that's interpreted incorrectly more often than the time. And this one here has the notion here, forces are always in equal and opposite pairs. So we use an analogy here. Let's say you run up against a wall. If you try to apply a force of 10 newtons, the wall doesn't like that. The wall is going to push against you, negative 10 newtons. If you push on the wall, let's say 100 newtons, provided that the wall doesn't break down, it's going to push against you, negative 100. Now the part that people interpret incorrectly here is, let's say I have an object, and let's say I apply a force going upwards. I have an FA, I'm trying to lift this object upwards. When I say equinopposite, I already mean there is an equinopposite pair. As, okay, you pull up, that's one force. The box pulls down. Pulls your hand down. That's what we mean by equinopposite. Notice that that part there has nothing to do with gravity. Well, now sure, later on there is a gravity force. Well, gravity also pulls down. Gravity pulls the box down. And strangely enough here, the box, just this force itself is already its equinopposite pair. The box itself is actually going to pull the entirety of the Earth towards it. The box pulls the Earth up. Now, why don't I see the Earth whoosh towards me? Well, the F net here is contingent on mass here. The mass of the Earth is humongous. The amount of acceleration, albeit the force is equinopposite here, the acceleration is going to be very tiny. We usually just say, well, tinier objects get actually pulled towards the Earth. So when I say equinopposite, I'm actually saying the arrows themselves, each arrow I draw has an equinopposite partner. But usually for the arrows we draw, usually we just consider, well, yeah, FG this way, yeah, FN this way, yeah, FA, things like that, right? We're not necessarily saying just because gravity is this has to mean the other one has to cancel it out. This arrow by itself is already equinopposite depending on the situation. Maybe I'm pulling it hard enough that it lifts off the ground. Maybe I'm not. Okay. So let's just work through a few questions here. I want you for this one here, calculate the friction coefficient, or calculate the mu for this situation. I'm just going to pull the object to the right and keep it simple for now. I'm going to pull it with 100 newtons. There's a certain roughness I don't know. There's a certain mu to that. The mass of this object here I'm going to give you is 50 kilograms. And I'm told that in this situation, this object actually is sliding along at constant velocity. Okay. Don't get scared about that constant velocity. Well, let's say constant velocity means there actually is no acceleration. A is equal to 0. And if there's no acceleration, Newton's second law, F net is equal to m times A. If the A is actually going to be 0, then that means the net force is actually 0. That means there can't be any overall wind. So let's do our free body diagram. What are the forces that act on this 50 kilogram? We did it in order. Let's do Fg first. Now this object we're told slides to the right. It neither goes into the ground nor pops off the ground. So therefore we can say there has to be a normal force. This is not the equinopposite part, right? The Newton's third law says just Fg itself is equinopposite. Now we're just looking sort of broader and we're saying, well, the Fn, yes, it has to cancel Fg, or else this object will go up or down. That's going to then give you a force of friction, and then we're actually applying a force of 100 newtons going to the right. So let's do that in order here. Let's do the y direction first. Fg, we always have a formula for, it's just m times g. So 50, assuming we're on the Earth's surface here, 9.8. That should give you 490. 50 times 9.8. So far, based on the masses, gravity is an attractive force pulling the box towards the Earth. It's 490 downwards. The Fn, we said, was a little bit lazy. The Fn just pushes what it needs to. It knows this object here just slides along. Gravity doesn't get its way. The ground actually supports you. The Fn is actually 490. Sometimes you say one of these is positive, one of these is negative. No trouble because we actually had the free body diagram there. Okay. Why we care about the Fn? Again, it's a sort of measure of how much the grooves interlock. To find out the maximum friction, Ff is actually equal to mu Fn. Now, normally we would be given a mu here. I'd multiply the 490 and I get a Ff, and we can go from there. This time, we don't know what the mu is. So far, I know 490 is the Fn. I need another way to end up finding Ff, and then I can do a little bit of algebra here and actually find mu. Well, let's backtrack here. There is no net force. There's no imbalance force. So far, the forces that we sort of didn't know here, I'm pulling 100 newtons forwards. I don't know the size of my friction force. And yet they tell me there's no winner. There's no imbalance force. So you can try all you want, bigger minus smaller, but nobody wins. That means 100 was just enough to keep it at constant velocity. That actually tells you the Ff here is actually 100. Again, you can avoid the worry of positive or negative 100 here because I have a free body diagram. So that actually tells you, well, if the Ff maxes out at 100, I don't know what the mu is. I'm going to multiply it by the 490, which is the normal force. Just divide out the 490. 100 divide 490 gives me a mu coefficient of 0.20. This number never really gets to be very big, but obviously if this number here is larger, it means the surfaces are more rough against each other. Okay. At this point here, let's just take a quick detour into pulley systems. Okay. That's the whole notion here. Pulleys, they act as systems. They actually act as one. So let's do a question here. Let's say I have a 5 kilogram object. It's hung over a free hanging pulley. I have a mass m here, and I'm told that the acceleration is 3.0 in the clockwise direction. because we are sort of hung by the string here, both of the masses have to move together. And because of this acceleration, we know this mass accelerates up 3 meters per second. This mass here accelerates down 3 meters per second. So we already know that the m needs to be heavier. That's why it can pull it downwards. As always, we want to start off with the free body diagram. So I'm going to have on this mass here, there is already an FG1. There is a tension in the cable, T1. The tension here is sort of the tautness of the string. This is going to be equal and opposite along the string here. There is a T2 going upwards. Well, T1 is the same as T2, so I'm just going to call it just one and the same T here. And then we're going to have an FG2 here. Anytime we're looking for FG, it's easy. It's just m times g. So this side here, it should be 5 times 9.8. So that one there should be giving you 49. Right. It's trying to go 49, it's trying to stop you. This side, oh no, we don't know this m here. Still, let's write the expression. If you know what m is later on, that's going to be m times 9.8. So we can just write that out here as 9.8m. And now what we're going to do first is we're going to look at the entire system all at once. Right? What's happening here is we have two forces that are trying to pull it clockwise. That's going to be the FG2 as well as the tension 1. Those two are fighting against. The FG1 is trying to keep it in the counterclockwise direction. The other tension is also trying to fight in the counterclockwise direction. So we can analyze this here as a side-to-side problem. So 5, we have an m. This way here you can see the tension force a little bit better. The tension force that was trying to make it go to the right actually cancels out the equal and opposite force. The tension force here trying to go to the left. When you study the entire system, the tension cancels out. So therefore, really, it is just FG1, which is pulling 49 newtons. It's trying to cause the whole system to go left, whereas my force is going to the right here at 9.8m. Let's take a look at the answer. Well, the answer is it accelerates 3 meters per second in favor of the FG2 side. So because I know the answer, the acceleration is this way. To avoid worrying about negative accelerations, we always just go bigger minus smaller. So if I were to write out an expression here, I know the F net is supposed to equal to ma. The tug of war this time is between the 9.8m, the FG2 is fighting against FG1. I go bigger minus smaller, so it would be FG2 minus FG1 has to numerically give you the mass of the total system times the acceleration. Let's just punch in the terms here. Well, FG2 is 9.8m. I still have no clue what that unknown mass is. For the FG1 is going to be 49. I still go bigger minus smaller. This has to equal to the mass of the whole system because both the 5 and the m have to travel together. I'm going to have a 5 plus m, and the overall win, I can keep the acceleration as positive as 3.0 meter per second squared. All right? So I'm going to keep working through this here. I'm going to distribute this 3 in. So we have 9.8m, just a little bit of algebra for us, minus the 49. This is going to equal to 3 times 5 is 15, plus 3m. Well, I can collect out my like terms. I can minus the 3m here, 6.8m. I'm going to add the 49 over. 15 plus 49 gives me 64. And therefore, using Newton's second law, I've been able to find what the mass here, 64 divided by 6.8 gives me 9.4 kilograms. Right? To measure actually these force of gravities as well, we usually use a spring scale. A spring scale essentially has a slinky. The slinky already has some natural length here. There's a hook on the end. If I put this mass here on the scale, it's actually going to pull down the scale. It's going to stretch out my slinky a little bit longer than it wants to be. So this one here has an L naught. It has an original starting length here. As I put my 9.4 kilogram object on, it's going to stretch my slinky out longer, farther than it wants to be. This is where we actually get Hooke's law come back here. So we have the slinky is now this delta x a little bit farther than it wants to be. It's that delta x here that f is equal to. Sometimes we say negative kx because it's actually the opposite, but we can avoid negatives using our free body diagrams. Okay, so that's how you deal with slinky style problems. We've been able to find the mass here. Usually the follow-up to this question here is to find the tension. For tension, we had applied Newton's second law for the entire system. For the tension force here, you can zoom in either on just the one side or on the other side here. The nice thing about Newton's laws here, we saw a little bit in the relativity section as well, that your physical laws here apply to the each object individually. So let's try the object on the left here. I have a 5 kilogram object. Earlier, the tensions had canceled out when I studied the entire system. So if I just look on the left side, I have a tension force minus an FG force here of 49. Right. This acceleration here, because I'm on the left side, the acceleration is actually going to be upwards. If I want to keep this as a positive 3, when I try to do Newton's second law on this left-hand side, F net is supposed to be equal to ma. I always want to go bigger minus smaller. In this case, again, the tension minus the gravity of 49 has to equal, this time I'm just focused on the one mass, so it's going to be 5 times the acceleration of 3. Yes, the tension is going to be created, it's going to be caused by the FG2, but because the system overall accelerates, this tension still has to be calculated for. So if you type in that number there, we get a 15, we add the 49 over, the overall tension force that we're getting is, I believe, 64 newtons. Try verifying for yourself. If you try the opposite side, try the 9.8 times the m of the 9.4 that we calculated here. Try FG2 minus tension is equal to the 9.4 again times 3. You should be able to get the same tension there. When we looked at a tabletop pulley question, I'm just going to allude to it here. Tabletop question, sometimes we found the silly situation. I'll let you work through this. Let's say it's a 3 kilogram object, and let's say I have a 1 kilogram object here. If this were a free hanging pulley, I'd say, well, no contest, the 3 kilogram object wins. But what's happening here is when we actually do a free body diagram, sure, the free hanging pulley, Fg2, m times g, there's a tension force here. It's actually not fighting against Fg1, right? Looking at the direction, the string actually tries to pull this object here off the table. It's actually between Fg1, we have an Fn, and we have a friction force. So for a tabletop pulley here, it's actually Fg2 fighting against friction. Especially if there's no mention of friction here, you can assume that the friction force is 0. Even a lighter object can actually pull the heavier object here. So I'm going to give you a number to this and let you try that out here. Let's say the mu coefficient, let's keep it tiny, let's say it's 0.10. So it's very, very smooth surface here. I want you to calculate the acceleration and the tension on the system. Tension along the string. Okay, you should have enough information for you to work your way through that a little bit easier because we actually have the mass term. Okay. The questions I want to practice with you here, I want to practice with you a slope problem. So now that if I'm actually on a ramp, this one you're going to do a little bit more in physics 12 as well, but let's just analyze through here. Let's say I have a 10 kilogram object. Let's say this object here is being pushed upwards. It was given a velocity of 30 meters per second going upwards. Let's say the coefficient of friction here, the mu is 0.25. Similar style question as earlier, although it's not a pulley style question. I want you to calculate the acceleration. That's going to be your connection to kinematics. And once you know the acceleration, I might ask you how far up the ramp until stopping. Right, so that's a more standard kinematic style question. I want to use my kinematic formulas and whatnot. As always, you want to start off with a free body diagram. I do want to give you the angle before you do that. So let's say this is 50 degrees. Okay. For a free body diagram, gravity does not care that you're on a ramp. So gravity always pulls straight downwards. Okay. Now, problematic thing here is in my regular coordinate system, that gravity would be perfectly downwards, but this object here is actually going sort of up and down along the slant. So what we're going to do is we're going to slightly rotate our coordinate system. Again, back to relativity, your physical laws will work in any coordinate system here. What if I rotated my coordinate system so my new x prime direction was actually sort of along the slope here? My y prime direction is actually vertical off the slope. That means the gravity that originally was fine, it was not diagonal, I need to find for you which part is actually into the slope, which part is actually down the slope. And for this stuff here, just be careful to draw your triangle nicely here. Some hints are one arrow has to be perpendicular, the other arrow has to be parallel to the slope. We're going to call this one here F in, as well as F down. And remember, we did some geometry here, 50 degrees. It actually amounts to 50 degrees there. So this one here, normally you can't memorize, so x is cos and y is sine. In this case, because Fn is always going to be the adjacent side, that's actually sometimes called the squeeze, is trying to keep it on the slope, and therefore it's just going to be Fg, in this case here, cos of theta, and the F down is going to be Fg sine of theta. So although gravity, right, gravity is m times g, 10 times 9.8, in this case is 98, only part of that 98 is used to go downwards because some of it is actually needed to actually hold it on the slope. So let's just work our way through with our numbers here. So 98 cos of 50, how much of it is squeezing it onto the ramp? Of that 98, 63 is actually squeezing it on the ramp. What about going down? 98 sine of 50. This one here gives me 98 sine 50 is 75. Right? We had to use Pythagoras to break that up. Right? So a squared plus b squared is ending up with c squared. We do have a normal force. The normal force pushes perpendicular to the surface. This time the surface is actually diagonal, so perpendicular to that goes directly against F in. And knowing this object here just slides up the ramp, it neither goes into the ramp nor pops off the ramp. The Fn is going to be the opposite of F in. So 63. To avoid worrying about who's positive and who's negative, just have a free body diagram with the arrows, where this one is pointing off the ramp and this one is pointing into the ramp. Why do we care about Fn? Is because then we can calculate Ff. The maximum friction force here is equal to a mu Fn. If the mu is 0.25 and the Fn is actually calculated to 63, notice it's not all of the 98. The 63 times 0.25, give or take a little bit of rounding here, my friction force maxes out at 16. Which direction does it go? It goes against motion. This time the motion is actually upward. I actually have a velocity going up this way. So I'm trying to slide upwards, meaning friction is actually downwards. So here's a part that a lot of people get wrong here. As you start looking at the net force, we have Fn canceling F in, so those are gone. We have a downwards force that's sliding it down. Friction is also trying to slide it down. Notice they're actually on the same team. Nobody is actually pushing it upwards. It was given a forward velocity, but my hand might be down here. If I'm no longer touching the object, I can't influence the object anymore. So the only forces that are acting on this problem here is we have gravity, the downwards portion, is pulling 75 newtons down. So F down is 75 newtons. And there's also a friction force that's also trying to oppose motion. Friction adds an extra 16 newtons. Because they both pull down the ramp here, they help each other. This time when I try to do F net equals ma, right, the net force is going to be given by the F down with friction. Those are the only forces that act on the object, and that's going to cause your overall acceleration to try to slow down your mass by a certain acceleration. So I just add those two there, 16 plus 75. In total, I have 91 newtons. Again, I don't need to worry about positives and negatives. I can see the direction. The net force, well, nobody's pulling upwards. The net force is definitely going to be down this way. The net force is actually 91. If that's an overall unbalanced force, and your mass was actually 10 kilograms, what's the acceleration going to be? So I just divide the 10 over. Acceleration is going to be 9.1 meter per second squared. And just looking at the sort of orientation here, this one here is actually down the slope, or down the ramp. And then when you get to your kinematic question here, well, now it's a basic question where your initial velocity, your v naught was actually, what did I say, 30 before? 30 meter per second. I know by the time it gets to the top, the v final is actually going to be at rest. We use force to actually calculate the acceleration. The acceleration is actually in the opposite direction. I need to now add that as a negative. Negative, it would have been 9.8, but now because we're on a ramp, it's only 9.1, given friction as well. We can do a fairly simple calculation. V squared is equal to v naught squared plus 2ad. The velocities will be positive, so final velocity is 0. Initial velocity was positive 30. The acceleration is against me, so negative 9.8. Again, the reason why it's smaller than 9.8 is because it's only the downwards part of gravity, even helped out by friction here. What is the overall displacement that we travel upwards? So let's try 30 squared. That's 900. I can move it over. Negative 900 is equal to negative 2 times 9.1 is 18.2. And therefore, the distance is 900 divided 18.2 gives me 49 meters. Because this object here had such a high positive velocity going upwards, even though the net force was directly against it, it's constantly trying to slow it down, it still makes it some positive 49 up the ramp. It doesn't stop in its tracks here. It does need to take a little while for it to come to a stop. Okay. So that's sort of the problems that we're going to look at in this section here. The one last section I want to just recap with you here is a notion of universal gravitation. Again, if you go on into physics here, you're going to learn gravity is actually not a force, but for the time being, we're just going to treat it as is. This formula here, Fg, force of gravity is equal to mg, was actually a slight simplification. We've been assuming we're on the Earth's surface. We've been assuming this one here was 9.8. This formula is actually a simplification of a much bigger formula. Newton's law of universal gravitation on your formula sheet. Fg is equal to g m1 m2 over r squared. We can see from this sort of correlation, you have this g here as a gravitational constant. Because this gravitational constant is 10 to the negative a whole bunch, we really don't see the effects of gravity until we start talking about planetary sized objects. It's just that for most of the questions, slope problems, lawnmower questions, elevator questions, we've been assuming that we've been near the Earth's surface. We've always been using the mass of the Earth. We've always been using the radius of the Earth. And we actually calculated in our lesson, the gravitational field strength ends up being 9.8. So if you know the field strength, if you know that around the Earth's surface, if you know that this g m1 r squared ends up pulling 9.8, the second that I tell you your mass, you just take the 9.8 times mass, and that ends up giving you the gravity force. Because gravitation here is going to be inversely proportional to the radius, although everywhere on the Earth's surface, the gravitational field will always be 9.8. If I go farther away, we'll do this more in Physics 12, as I go farther and farther away, the gravitational field actually gets weaker. If I could hypothetically get even closer to the Earth's surface, my gravitational field strength is even stronger than 9.8. All it's done here is it's saying, this is the force that you would feel. You still need to tell me what the mass is, but take the mass times the gravitational field at that distance, and that'll end up giving you the force. Remember, the formula itself was not all that hard, but it was a little bit of practice trying to type in the numbers. Usually they'll give you constants of the mass of the sun or the mass of the Earth, calculating for one unknown variable. The question I'm going to do for you here is, this tells you the force of attraction between, let's say, m1 and m2, separated at a distance r. Maybe this is the moon, that's sort of one radius away. Sometimes you even use d for that. They can also ask you sort of do it by ratio. What if I doubled the size of m1? What if I tripled the size of m2? And what if I made the r here, let's make r a quarter of what it was. Right, so I actually pull it in closer. Well, in this situation, you're going to still try to do this formula. Fg is g mm over r squared. So g m1 m2 over r squared, you just try to punch through your changes. So the m1 now is twice what it used to be. The m2 is 3 times what it used to be. I'm going to pull that 2 and the 3 multiply going up front, so that's going to give me a 6 up front. Then, oh no, I took this radius here. Instead of these planets here being so far away, I actually pulled this planet in that were actually only a quarter of the distance. So these planets here are actually a lot closer together. The r is actually only a quarter of what it was before. Now, because the radius here is on the denominator here, as I shrink the separation distance, I'd expect the force of gravity to go up. It's also going up by a square of it. So this r here ends up being a quarter of what it was. Two numbers squared is going to be a quarter squared and r squared. So this bottom part will actually be 1 over 16 r squared. When I have 1 over a fraction here, it actually multiplies upwards. So I actually get 6 times 16. We actually have 96 times what the force of gravity is. So based on the changes that I gave you here, yeah, doubling the mass here would have doubled gravity. 3 times the mass here has tripled gravity here, but it was that really bottom part here. If I make these a quarter of the distance that they were based on this square, that ends up contributing a 1 over 16 change in the force of gravity. It's 16 times stronger. 16 times 6 is 96 times more intense than the original gravitation. Okay, so have a look at a few of those problems and let me know if you have any questions. Thanks, guys.